on the cloud. Okay. All right, so today we're gonna do more examples on limits to infinity and limit, infinite limits. And then after that, we're gonna move to our new concept, continuity. So let's first talk about example 24 on slide 39. So this question, we ask you to compute limit of x cubed minus 5x plus 7 over square root x squared minus 3x. First of all, if you use my technique that we just discussed last time, so you can see that on the numerator, we have the highest degree is equal to 3. On the denominator, we have the highest degree x squared here, but after I take square root, it should be degree 1, right? Well, that means the top is heavy. So you can see here that the top is heavy. And then once you know that the numerator is heavy, and then so our guess, the answer is going to be plus or minus infinity. So this should be the first thing that you trying to figure out. So you should guess your answer first, and my guess is the answer must be plus or minus infinity because I see that the top is heavier compared to the bottom. So because I guess that my answer is going to be plus or minus infinity, so I will use the technique that we just learned last time to show that it is equal to plus or minus infinity. I am going to show that first, limit of 1 over fx go to 0, right? And then second, I have to show when x go to the point that I want, fx just greater than or less than 0, and then I can conclude what I want. So here I'm gonna let fx to be x cubed minus 5x plus 7 over square root x squared minus 3x. Well, this is my fx, and then I'm gonna show two things. So first, let's consider the limit of 1 over fx. I need to show that this thing goes to 0, right? So for this context, x go to negative infinity. So that means I want to compute limit of square root x squared minus 3x over x cubed minus 5x plus 7. Well, when you show your work, you have to show me how to do this question by, slowly. So first of all, you have to divide everything by x cubed first, because this is the highest degree, right, for your term. So you're gonna divide everything by x cubed. So that means on the denominator, I am going to have 1 minus 5 over x squared plus 7 over x cubed. So I divided everything by x cubed on the denominator. On the numerator, I am going to divide everything by x cubed as well. All right, so, well, and then the next step is I am going to pull out my x squared. So limit x go to negative infinity. So I am going to pull out my x squared, and then I have 1 minus 3 over x here over x cubed. 1 minus 5 over x squared plus 7 over x cubed. And then after that, you can see that if I pull out my x squared, so my x squared takes square root, I am going to get absolute value. So that the thing is going to be this, and then I get absolute value of x, right? And then when x go to negative infinity, so my absolute x, it's going to be negative sign. So I have negative x 1 minus 3 over x cubed, and then everything over 1 plus 5 over x squared plus 7 over x cubed, And then after that, now it is ready to compute. So this is negative x cancel with x cubed. So I have x squared left. And then you also have that 1 minus 3 over x, 3 over x go to 0. And then on the bottom, 5 over x squared go to 0. And then 7 over x squared go to 0. So once you have everything ready to compute, so you can see that at the end, you're going to have limit of 1 over x squared, which 1 over x squared here go to 0, right? So, and then multiply square root 1. So on the top, you get 0. You get 0 because you have x squared here. So that means 1 over x squared going to go to 0. And then under square root sign, so you get 1. So that means 1 multiply 1 over x squared, and then yeah, that is 0. And then in the denominator, so you have 1 minus 0, 0. So, well, anyway, you get 0. So it's a long story, but limit 1 over fx, you get 0. And then number 2, so now once you get that 1 over fx go to 0, you have to figure out that the function that you have here, is this function positive or negative? Well, when x goes to negative infinity, so by this I mean when x go to negative infinity, so that means x less than, so you can just pick some number that this is very small. So I am going to pick negative 50 million. Well, if you think this is not small enough, so you can pick anything that is small enough for you. So you can figure out the sign of x cubed minus 5x plus 7 over square root x squared minus 3x easily. So you can see that when x less than negative 50 million, well, what happened? So on the numerator, so you have x cubed. So the big negative thing, you cube it, so you still get negative thing. And then you minus 5 times x. Well, the negative 5x is not going to, the negative 5x doesn't matter because anyway, it's going to be dominated by x cubed, right? Because x cubed is so big in terms of negative things. So it's going to dominate everything on the top. So at the end, well, the thing that you have on the top here, this is going to be negative because x cubed is so big. And then you know that x is very, very small, right? And then on the denominator, you have x squared minus 3x. Whatever you have here, you take square root sign, so it's going to come back to be positive, right? Because under square root sign, you need to have positive things. So, well, that means at the end, you're going to come back to positive thing. So you have the ratio between negative and positive things. So this is less than 0. And then your conclusion is going to be because of 1 and 2. So you conclude that limit of fx that you want when x go to negative infinity, this is equal to what? Negative infinity as well, right? Because you show two things, that the limit of the reciprocal of f is equal to 0 and also fx less than 0. This is what you have to do when you show your work. So if you guess that your answer is plus or minus infinity, so you need to show your work by checking two things here. Does it make sense? All right. So I think we are stable now, 42 students here. So 8:15 now. So I just did a review on what we did last time. So this question is not easy. This is the medium one to hard one. So I mean, this is the question that if you see on the exam, this is going to be the question to cut B plus or something like that. I mean, student who did this thing correctly should get B plus or A or something like that. I mean, This is not the easy one, but yeah, it take some, some work to get to the correct answer, and yeah, it is a good one. So let's move to example 25. So that will be the last one for limit to infinity and infinite limits, and then we're gonna move to continuous function. All right, so the last one, example 25. So this is our O exams, and it could be repeated again this year because this is an interesting question. So let's look at example 25. So we said that we want you to compute limit of square root x cubed plus x squared plus x minus x. So the first thing that you can observe is this thing, when x go to positive infinity, this thing go to net infinity, right? And then when x go to infinity, this thing go to infinity as well. So at the end, you're gonna have negative infinity minus, infinity minus infinity. So you cannot answer anything from here, because when you see infinity minus infinity, so you don't know which one is bigger, right? So you still cannot, you still cannot conclude anything from here. Well, how do you know that the first infinity is bigger than the second infinity? So we have no theorem to show that. So we're gonna just need to simplify it first. So the point is that if you see infinity minus infinity, you just need to simplify first. You cannot do anything for now. So the thing that we are going to do is we are going to simplify this thing. So I am going to multiply by its conjugate, right? Because every time when I see this pattern, well, I can multiply by its conjugate. So I'm gonna do this. Well, I multiply by its conjugate first, right? And then after that, I simplify it. So I'm gonna have x go to plus infinity. And then, well, on the numerator, I have x cubed plus x squared plus x, and then minus x squared. So this is from a minus b, right? Plus multiply a plus b, right? And then after that, I have this, and then on the denominator, I have square root x cubed plus x squared plus x plus x. Well, you can see that x squared cancel. And then for now, you can see that the highest degree on the top is 3. The highest degree in the bottom is 3, but you have to take square root, so it's 1.5. So that means, again, from here, you observe that the top is heavy again. So once you observe that the top is heavy, then I am going to guess that the answer is going to be plus or minus infinity. So if the bottom is heavy here, you're gonna guess that your answer is 0, right? And I mean, if your highest degree for the numerator and denominator are balanced, so you can use the coefficient as your answer. And then here, I guess that my answer is going to be plus or minus infinity. So I'm gonna let my fx to be x cubed minus plus x over square root x cubed plus x squared plus x plus x. So this is a function that I want to compute limit. And then number 1, limit 1 over fx, where x go to plus infinity. This is going to be limit of, so this is the routine work. So you're gonna just move this thing up. Well, we have done this thing for so many questions, so you should be able to do it now, right? And then after that, I divided everything by x cubed. So on the denominator, I am going to have 1 plus 1 over x cubed, x squared, because this thing I divided everything by x cubed, and then on the numerator, I have square root x cubed plus x squared plus x over x cubed. I keep this thing first, and then plus 1 over x squared. So you can see that at the end, this term that I just cloud in green, so they will go to 0. So what I am worried is only the first term that I have square root side there. So what I'm gonna do, I can, well, for this question, because x go to plus infinity, well, I'm gonna, because x go to infinity, so I know that x cubed is just square root x to the 6, right? To the 6th degree, because x go to infinity, I can use this thing. So I'm gonna do limit x go to plus infinity, and then, well, I keep everything first, and then I have x cubed plus x squared plus x over x to the 6th power. This is another way you can do the problem. So some of you love to pull out x cubed from the square root. You can do that too, but what I did here, I just switched my x cubed to square root x to the 6th power. Well, you can do this thing to just, you know, put x cubed inside the square root sign. Because you can do this because this is x go to plus infinity, so you don't have to be worried about the negative side. And then after that, well, x to the 6th power gonna cancel something inside the square root side, right? So you're gonna get x go to plus infinity, and then this gonna be 1 over x cubed plus 1 over x to the 4th power, 1 over x to the 5th power, and then plus 1 over x squared, and then 1 plus 1 over x squared. So here it's easy now. So everything go to 0 on the numerator, and denominator go to 1. So at the end, you have 0 over 1, which is 0. So you're good, right? And then number 2, now you have to figure out the sign of fx. So what is the sign of fx here? Well, it is very easy, because when x go to plus infinity, that means x is super big, right? So I would say, yeah, let's do x bigger than 10 billion. Well, you can pick any number you want, but just make sure that it is big enough, because it's go to infinity. So I'm gonna pick x greater than 10 billion, right? Well, this number doesn't matter. You can pick 1, 2, 3, 4, 5 anyway, but make sure that you pick the one, after this point, the sign doesn't change. So after x greater than 10 billion, so if you plug in the big number into this function, anyway, you're gonna get positive sign, right? Because it's x cubed plus x, and then over something, everything in the fraction here, this is all positive, so it's gonna be positive anyway. So your conclusion gonna be, so the sign limit is plus infinity, right? Because you show that the limit of the reciprocal thing is equal to 0, and also your function fx is greater than 0, so your conclusion gonna be plus infinity, or i.e. limit of that, well, that I given in the problems here, this is equal to plus infinity. All right, so any questions on infinite limits and limit to infinity? All right, type in the chat if you have any questions. If not, we are going to continuity. Make sense? So we have done so many examples on infinite limits and limit to infinity, and this is a big part for chapter 1. So make sure you know how to write solution correctly. So your homework that you have to submit on Monday, you can see that question 3. You have to show your work when you compute limit, and this is our expectation. You have to write solution, the complete solution like this. So don't skip step, because if you skip step, well, I cannot guarantee that you're going to get full credit if you skip step, because it depends on the grader. So we have the grader for this class, and if the grader said that, hey, you skip step, and then they give you like the point that you miss some credit, well, I cannot help anything, because that is our standard. All right, so if you don't have any question, we're gonna move to next topic, continuity, which is the last one for this chapter. All right, no questions? All right. So let's move to the last concept of this chapter, which is continuity. So you have seen so many times that, well, sometimes you're gonna have the function that you see in the picture on the right here. So the one that you have the left hand limit, you have the right hand limit, but the limit does not exist at one point. Well, this is the example of the function that we call not continuous. So continuous function is the one that you see on the left here. Well, by the name of this property, so it's give us, well, our background already. So continuous mean like in the picture. So if you think in terms of geometry, so this is the interpretation of continuity. So it's mean geometrically. So you can think of a function that is continuous at every number in the interval as a function whose graph has no break in it. So the key point is the graph can be drawn without removing your pen from the paper. So that means if you have the function, and then you don't have to, remove your pen from the paper. It's keep going, and then you don't have, well, there's no break in it. So this means the function is continuous. But as long as you have the function that, hey, I have the function and then it stops somewhere, and then you have to, well, for now, I have to just remove my pen from the paper, and then I just draw another function here. Well, this is the same function, but you can see that, well, at this point, x equal to a, it is not continuous. So that means the function is not continuous. In terms of math, so you need to memorize. I say memorize. So you have to memorize these three conditions for continuous function. So we're going to say that f is continuous if first fa is defined, second limit when x approach a exists, and the last one is number one and number two, they are equal to each other. This is why we say that plugging a number into the limit makes sense sometimes, because when you compute this thing, let's say go back to when I taught you on the limit law. So I say, hey, students, when you have limit x squared plus 2x plus 5, where x go to 2. Well, I told you that, hey, you have to use limit law, limit x go to 2, right? And then x squared, and then plus limit 2x, x go to 2, plus limit 5, x go to 2. And then you use limit law again. So it's going to be limit x when x go to 2, and then square, and then plus 2 times limit x, x go to 2, and then plus limit 5, x go to 2. And then after that, you just compute. This is 2 square plus 2 times 2 plus 5. This is the way we compute limit by using limit law. This is the one that we just learned in section 1.3. But because we know that the function here is continuous, this is continuous function. That means this thing is also equal to f2 because the function is continuous. By the property number 3 here, if you want to compute limit, it's going to be the same thing with you plug in number 2 into the function because the function is continuous. So the continuous is the good property because it makes our a lot easier because now if you see a continuous function, instead of computing the limit by using limit laws, we can just plug in number here. And this is what you just learned in high school. We just use all the time, but well, we can do it actually because of the continuous property, but we just learn it now. Does it make sense? So this is, so some people, I mean, most people in the world, they're gonna forgot about continuity, that continuity has nothing. So, but this is a very important concept in terms of math, but we use it all the time, but we just didn't express it. So the point here that I teach you today, I want you to memorize the definition of continuous. So first, FA is defined. Second, limit exists. And then if number one and number two equal to each other, then you conclude that the function is continuous. So there must be three ways that the function is not continuous. So let's look at this. So the function, well, I give you the graph here. The function could have a break in terms of not continuous. You have three ways. So look at x equal to 1. So the x equal to 1, we say that the function f is not continuous at 1 because f1 is not defined. So in terms of continuous, so f1 need to be defined, right? So at x equal to 1, condition number 1 is not met. So, well, the function is not continuous. As x equal to 3, we can see that limit of fx when x go to 3 does not exist, right? Because the left hand limit and the right hand limit are not equal to each other. So the function is not continuous at x equal to 3. And then at x equal to 5, well, f of 5, which is defined somewhere above, you know, above the line, right? So this is not equal to limit of fx when x go to 5. So the function is not continuous at 5 as well. So this is the example that you can have three ways of discontinuous property. So the first one is f is just not defined. So the second one, limit does not exist, or they are both exist, but they are not equal to each other. So this picture I just add into the slide just now because, you know, our recent story this week. So if you wanna show that f is continuous at a, you need 3 conditions. So you can just memorize by just using your 3 finger here. So fa exists and limit exists, and then if they are equal to each other, then yes, so the function is continuous. So we have about 20 minutes left here. So we're gonna do a few examples. But before we move to some examples, so do you have any questions? Type in the chat. Any question? All right, just a bit to check that you are awake now. Just type in the chat, check in, so I know that you attend the class today. So go from now. All right. Yeah, okay, I mean, you can type anything. Hi, it's okay. Hello. Well, just make sure that you just, you know, check in today. So I have the record. All right, next, I am going to go to the examples. All right, so the examples for the continuous function is super easy. You will see in a minute that the example we have is so easy, and the key point is you just need to show 3 things. All right, so let's start by example 26. I have a function f, and I want to show that I want to verify that f is continuous at -1 or not. Well, I will show you how to do this thing by using the full solution. So when you do the homework or the exam, you should show your work completely like this. So first of all, I have my function x, right? And then to show the continuous property, so you need to show three things. So first, you need to consider f of -1, right? Because you want to show the continuous at -1. So you trying to find f -1, and this is 1, right? Because this is from the problem that f of -1, 1. Okay, done. Number two, you need to find limit of fx where x go to -1. And this thing, you can see that when x go to -1, so it's mean around -1, you're going to use the function x squared plus x over x plus 1, right? Super easy. And then here you can see that if you plug in -1, so you're going to get 0 over 0. So you have to use some technique, factoring or conjugate or what else, squeeze theorem, whatever you want. But here you can see that you just need to factoring. So if you factor x one time, so you're going to have x over x plus 1, and then this cancel. So x plus 1 cancel out. So you're going to have limit of x where x go to -1. This is just -1, right? And then once you have 1 and -1 here, number 3, you can conclude that f -1 equal to 1, which is not equal to -1. But -1 is limit of fx where x go to -1. Well, because of this condition number 3 is not met, so we conclude that f is not continuous at x equal to 1, or at x equal to -1, sorry. Well, this is what we expect from you to show your work like this. So every time when we ask you to show continuous property, we'll show 3 things, 1, 2, and 3, as I show you on the slide here. Well, if all 3 conditions are verified, so you can conclude that the function is continuous. All right, so let's do more example. Well, for this part, continuous function, this is going to be super easy. So you don't have to be worried a lot, because we're not going to ask you something hard to compute limit, you know. So let's try to do example 27. So I want you to solve for the constant c that make your function continuous at x equal to 4. All right, so I know that if I want the continuous property at x equal to 4, in order to get continuity at x equal to 4, what we need is we need f4 equal to limit of fx when x go to 4, right? I mean, this is the condition that we need. If we have this thing, so we have a continuous function at x equal to 4. So we're going to start from there, and then we're going to get the equation that we can solve for c. So first of all, let's compute f of 4. So f of 4 is what? So this is equal to, well, you have to use the cx plus 20, right? So that means you plug in x equal to 4 there. So you have c times 4 plus 20. This is going to be 4x plus 5. Oops, sorry, 4c plus 5. C plus 5. All right. Am I right? Yep. And then after that, just stop here first. And then you're trying to compute the limit. And then you see that limit. To compute limit now, you need to do the one-sided limit, because the right-hand limit, you're going to use the one that I highlight in yellow. The left-hand limit, you're going to use the one that I highlight in orange, right? They use different function. So we're going to do when x go to 4 from the left. So that's mean limit x go to 4 from the left, which is x squared minus c squared. And then I can plug in number 4 into the function now. So this is 4 squared minus c squared. And that is 16 minus c squared. All right. Well, if you want, you can try to compute limit fx where x go to 4 from the right. But this is optional because if you try, this is going to come back to the same thing that you have with f4. So it's going to be 4c plus 20, which you already have it from f4. So this line is optional, but well, if you want to do it, you can. And then after that, you can say that the thing that I highlight in green here, they must be equal to each other in order to hold the continuous property. So we have c times 4 plus 5 equal to 16 minus c squared. I don't know why I factor this thing because it's make the world a lot harder. So I can delete this thing to 4c plus 20. That's better. So you don't have to simplify, I think. So and then you have c squared plus 4c plus 4 equal to 0, which is c plus 2 square equal to 0. And then that means c equal to negative 2. So this is your answer. C equal to negative 2 gonna be the answer that make the function f continuous at x equal to 4. All right, so c plus 2 squared, this is c squared plus 4c plus 4. Okay, I am good now. All right, sounds good. So that means c equal to 2 is the answer. Right, so you can see that, hey, the continuous property, this is easy. So I would expect everyone can complete the continuous problem easily on the homework. So the homework, you're gonna see question 2. That is the question we ask you to show something about continuous function. All right, so more on continuous function. So you already know that, well, the function f is continuous if this condition holds, right? This is why we say that you can plug in the number if the function is continuous. And then sometimes in the future, maybe you're going to see the word function is continuous from the right and function is continuous from the left. Like for those of you, well, I think you are nano engineering students, but for those of you who do the probability and statistic thing, well, at some point when you learn probability, you're gonna learn the cumulative distribution function. And at that point, the function is not continuous. But the distribution function in probability theory, so the function is continuous from the right. So we're gonna use the word continuous from the right. So the word continuous from the right means sometimes your function gonna be something like, well, let's say I have the function like this, like the step function. So you can see that the function is not continuous at the point x equal to a and x equal to b, right? But even it is not continuous, it has some good properties because, well, at each point a and b, when the continuous does not hold, you see that the pattern is the point fa and fb here. So it is equal to limit from the right. So if you have that case, so we're gonna say that the function is continuous from the right. So we are not going to focus on continuous from the left and continuous from the right for this class, but this is gonna be useful for later. I am not sure that nano engineering student, you have to take probability or not, but when you learn probability and statistics in the future, I mean, for sure, electrical engineering and mechanical engineering or something, they have to do it. But for those of you who maybe you have to switch the major sometime, I mean, in the future, I don't know yet, but well, you're gonna see the word continuous from the right, and at that point, you can come back to see, hey, that's mean the right hand limit is equal to FA. All right, so another thing is, well, if F is continuous at any point, every point in on the interval, you're gonna say that the function is continuous on the interval. So just simple like that. And then if you have two functions F and G, well, the sum is, and then they are both continuous. So the sum gonna be continuous as well. The difference gonna be continuous as well. The constant of the function is continuous as well, or the product or the quotient. You can use anything you want. Well, you can manipulate the function F and G, and at the end, well, once they combine, so the given result is still continuous. Well, the good thing is number 5 here. Once you know all the theory about continuous function, well, we're gonna wrap up that the polynomial and the rational function, they are always continuous. Very good, right? That means once you face the polynomial or rational function, they are continuous. Yes. So that means when you do the problem and then they ask you to check the continuous function, and then you don't have to be worried when you see polynomial and rational function. It's continuous on its domain. All right. So I want to show you what I mean by looking at another example here. And then we're going to come back to, and then we're going to stop, and then we're going to come back on Monday to complete the example. So let's see, I have 28 here, 29 here, and summary. So let's do example 29 today, and then we're going to come back to 28 on Monday, and that's all for chapter 1. All right, so let's do this question. I want to check that F is continuous on its domain or not. Show your work clearly on each step. So let's first trying to do this question. So at x equal to 2, this is the point that you have to check the continuous precisely, right? But you can see first that if x less than 2, then fx equal to 10 minus 3 x squared, which is continuous. Right, so you're done. Well, how do you know that this is the function 10 minus 3x 10 minus 3x squared is continuous? This is polynomial, right? It is continuous because it is a polynomial. One second, I say polynomial, yes. Polynomial. All right, so that means the function is polynomial. So yeah, fx is continuous. And then when x greater than 2, then fx is equal to 8 minus x cubed over x squared plus 2x minus 8. This is continuous because it is a rational function. The point is, you don't have to check the continuous property where x less than 2 and where x greater than 2, because the function is polynomial and the function is a rational function. So the only point that you have to check the continuity is x equal to 2. So if x equal to 2, so what happened when x equal to 2? So you can compute f2, and f2 is going to be 10 minus 3 times 2 square here, so which is 10 minus 3 times 4, which is negative 2. So you have this thing, and then after that you need to compute limit when x go to 2. right? So you need to compute the limit when x go to 2. So let's see if you can do this thing. All right, so we're gonna compute the limit when x go to 2 of fx. So for sure, I have to do left hand limit and the right hand limit. So the left hand limit is easy because this is going to be the same thing with f2. So I have -2, right? And then for x go to 2 from the right, so I am going to have 8 minus x cubed over x squared plus 2x minus 8. So at this point, you can factor. So on the denominator, you can factor this is x minus 2 and x plus 4, right? On the denominator, this is easy. But on the numerator, how do you factor 8 minus x cubed? Number 8 here, this is 2 cubed, right? So, and then once you have a cubed minus b cubed, so you're gonna have, well, recall from the basic algebra, you have a minus b times a square plus ab plus b square, right? If you are not sure that you are correct, so you can try to, expand it and then check that this is correct or not. So I think this is correct, right? Because after I expand this thing, so you're gonna see that they cancel and then we get what we want. So that means we have 2 minus x here and then 2 squared plus 2x plus x squared. And then after that, well, I have 2 minus x here, cancel with x squared, x minus 2 here. So I have -1. And then I plug in number 2 here. So I have, on the top, I have 4 plus 4 plus 4, which is 12. And then in the denominator, I have -6, which is 4 plus 4 plus 4, which is 12 over -6, which is -2. So you can see that limit exists and equal to 2. So because limit when x go to 2 exists and equal to 2, and also equal to f2, then the function f is also continuous at x equal to 2, as a equal to -2. Oh, sorry, at a equal to 2. Well, all right. Well, conclusion. So conclusion here on the top. Well, f is continuous on its domain, which is a real number r, right? Because you already checked that when x less than 2, the function is continuous. When x greater than 2, the function is continuous. And when x equal to 2, the function is also continuous, right? Well, that is how to show the continuous on the interval. So you can use the fact that the polynomial is continuous and rational function is continuous to help you to check the continuous on the interval. All right, we're gonna stop here for today. I think you have the class at 9 a.m., right? So you have to switch to other class, like intro to nano or something. So let's stop here and then we come back Monday at 3 p.m. So if you have any question, let me know. Well, on the chat now or on email or in live group. All right, thank you everyone for attending today. And if you have any questions, just let me know. Sounds good? All right, bye. Thank you.